Welcome to Shanti-Peace for Mathematics. In this video, we'll trying to learn what is the mean of a Rolle's mean value theorem, and we'll discuss a proof for the mean value theorem, Rolle's mean value theorem. So before going for the statement and the proof of the theorem, let us understand very fundamental concepts which are required to see what is Rolle's mean value theorem is. So if you have given any function f which is defined from a to b, then as per the definition of the function, we'll say that for every x is in a, there exists a unique y it is in b such that f of x is equal to y. If your a and b, both of them are the subsets of a real number, then we are able to plot the graph of this function, and as per the graph, it's saying that the graph of the function, if you plot any vertical line, and if you want to see that graph is a graph of the function, then it has to be intersect with the graph exactly at one point. That is the meaning of the unique y belongs to. For example, I will give you some questions here. Let's say the first graphs I am drawing in this way, the another one I am plotting with this way, and the third one I am plotting in this way. Then in these three graphs, you can say that this one is not a graph of the function. This is a graph of the function because you plot vertical lines here, that is always intersect with exactly at one point. But when you plot a vertical lines for this one, it will intersect at 3 points here. So it is more than 1 point. So that's why this is not a graph of the function. This is also a graph of the function. So whenever you plot any graph of the function, it will always intersect any vertical line with exactly 1 point. That is the definition of a function if you see geometrically. This question which I have drawn here, it was asked in one time in NET examination in the part A. Now the second thing we need to understand to discuss the Rolle's mean value theorem is the continuity of the function. When you can say a function is continuous, that means you can plot a graph of the function without lifting your hand. These are the two graphs of the function, and both of them can be plotted without lifting our hand, so that both of them are continuous functions. For example, if I can draw a graph of the function like this, this is my x-axis and this is my y-axis, and this is the graph that I am plotting. That is, this is the function, and then it will be like this. Suppose this is the graph. Then at this point, the function is discontinuous because when I plot the graph, I have to lift my hand to that. So it is discontinuity at that point is there. So that is the meaning of discontinuous function and the discontinuous function. The third thing that you need to understand, what does it mean of a differentiable function. So for that, I'm just giving you a concept. Whenever I ask you a question that give me example of function which is not differentiable at one point, then everyone gives me example, it is mode x, because a graph of the mode x that we know is this. So it just is my plotting error is there, but this is the point 0. So that point 0 at the point 0, this function is not differentiable. That is f of x is equal to mod x. The function is not differentiable at this point, 0 point. Why? But you can see the graph, it having the corner at that point. Or in another sense, I can say that at that point, the function have more than one tangent. So whenever you have a graph and it have a corner at some point, then that function is not differentiable at that point. For example, in the first graph which I have plotted, there is no corner, or I can say every point is having the exactly one tangent. Or another way is looking at or saying it is the curve or graph is a smooth curve graph. But in this graph, you can see that at this point, the function have a corner. So at this point, the function is not differentiable. Here is also there is one corner is there. So at this 2 point, this function is not differentiable. So by looking at the graph, you can say that the function is differentiable or function is not differentiable. So that is the most important things that I have talked. Let us recall what we did. First, I have told you that you can, what does it mean of a function? A graph of the function always intersect with any vertical line with exactly one point. The second thing that we have talked is a continuous function. That means you have to plot a graph of the function which is continuous without lifting your hand. The third one that we have talked is if the function is not differentiable at some point, then there has to be some corner is there, or I can say a graph is not a smooth graph, or I can say that at some point the function or the graph have more than one tangents. Now with these 3 ideas, I'm giving you one task here to do it. Let's say this is my x-axis and a y-axis. So this is my x-axis and this will be my y-axis. I'm fixing one horizontal line, and on this horizontal line I'm pick up 2 points. Let's say this is the 2 points A. That means this is my A and this is the point B. Now I'm giving you a task that you can plot any graph in between joining these 2 points, which has to be continuous as well as differentiable. So as you know that it is a continuous, that means that there is no gap in between the graph, and it is differentiable, that means that there will be no corner, or I can say a graph should be smooth curve. So pause this video and plot in your notebook or whatever you have. In that you can plot that graph as per your convenience. If you want, you can plot more than one graph, more than 2 graphs, no problem with that. But pause this video and try to do this exercise. Hope that you have done with your graph, and maybe some of you have plotted. Let me draw in different. So some of might be have a plotted like this. Some of them you might be have plotted like this, smiley. Some of them, those who are lazy, they might have plotted like a straight line joining these 2. It has to be a function, so you cannot go back where you have started, and there has to be no corner. And some of you might have a drawn that might be this type of figure, no problem with that also, whatever. So everyone has a different graph in their hand. But what is the observation that you can make out? Let me draw it here. In this, I'm plotting like this. I'm plotting at 3. This is a smooth thing. Okay, so it is not a corner. So I'm plotting like this graph. And you can just observe what is happening. In this graph, you will find always one tangent which is parallel to x-axis. So these are the different points on the graph of this function. Now whatever the graph you have plotted, on that graph, you will always find one point at which the tangent at that point, it is parallel to x-axis. That means if you have here in this graph, you can just observe that at this graph there is a tangent which is parallel to x-axis. Here at this point you will have a tangent which is parallel to x-axis. Here at this point you will have a tangent at which is parallel to x-axis. If you have plotted the graph like this, you have like this. If you have plotted like this, you have. Here all the points are satisfying. That means at this point there is no tangent, but because the function is constant, but it is the constant function which is parallel to x-axis. Here you will have two tangents which are parallel to x-axis. And any line which having the tangent is parallel, any line which having the slope which is parallel to x-axis, that slope has to be 0. And if you have a function y is equal to f of x, and if you want to calculate the tangent at any point, then we know that that is the application. That means you can calculate with the help of its derivative. And a tangent whose derivative is 0, that means it has to be f dash of c is equal to. So if I can call it this point is a c point here, then this coordinate of this point will be c comma f of c. At this point, the function have a tangent which is parallel to x-axis, which is nothing but its derivative at that point will be 0. And that is exactly a Rolle's mean value theorem is. So what are the assumptions we have taken here for this to see this theorem? The first assumptions we have taken that the function has to be continuous over some interval AB. The second assumptions we have taken, it is the function has to be differentiable at the point AB or in the interval AB. The third assumptions we have taken is this 2 points has to be on the same line. That means its y coordinate has to be same. That means that a comma f of a is this point and b comma f of b is this point. Then you will have f of a is equal to f of b. Then you will have exactly or maybe some more points, but it can be said that at least one point which is in between AB, such that a function derivative is 0 at that point. So that is the Rolle's mean value theorem is, and let me state what is that theorem here. That means let f from AB to R, that means I am considering a function whose domain is an interval, closed interval to R, be a function satisfies the following conditions. The first one, f is continuous on closed interval AB. Second one, f is differentiable on open interval AB. And the third one is f of a is equal to f of b. That means their endpoints whose y coordinates will be 0. Then there exists. So maybe this point C is at least one point is there in open interval AB, such that f dash of C is equal to 0. The f dash represents the derivative of the function. And this theorem is known as Rolle's theorem, or in title I can say a Rolle's mean value theorem. Why it is mean value? Because in between this interval AB, because it is a mean value between this interval AB, at this point it will have a 0. its derivative has the 0. Now let us try to prove this statement. And if we can observe what will happen at those points where this derivative is 0, it is either a maximum point or it is a minimum point. If it is in between this interval AB. So that is actually an idea to dealing with this theorem is. So let us try to prove this statement. What is given? Given is a function, given that the function f is continuous on closed interval AB. Since it is continuous on a closed interval AB, and there is one result is saying that any function which is continuous on closed interval AB, then that function is bounded function. So I can say that the f is bounded on closed interval AB. Since it is a bounded function, it has a maximum value and it has minimum value. So therefore I can say that, and also I can say that not only it is bounded, but it assumes its extreme value inside this interval AB. So that means there exists a point, let's say C and D, which belongs to open interval AB, such that I should not write, therefore it has to be n, such that m, which I can say it is a maximum of f of x in the interval open interval AB, such that is f of c. And if I can consider the small m, which is a minimum of f of x, which is in the interval AB, entire interval AB, such that is f of d. So this is the assumptions we are taking. Now what are the situations it will occur? The first one, as it is given, f of A is equal to f of B. Unless function is constant. If it is function is constant, what will happen in the case of, if the function is constant, it is automatically establish the result, because if the function is constant, we know that a constant function will always has the derivative is 0. So all those points where the function is constant will have this. So we can say that if f is constant, then a theorem get established itself, or I can say it is theorem is proved automatically. Now as this f of A is equal to f of B, a value of f of x should be either increasing or decrease as x move from A to B. So if your x is moved from A to B, then f should either increase or it may decrease, and then again, so that is a movement is there, but has to be going up or it going down. So if it is the situation like this at this 2 point, so that is a situation where the function is going up or it will be going down. As we have considered now, the function is not constant, because if it is a constant, so if I can say if f is not constant, then as f of a is equal to f of b, the value of f of x should be either increasing or decreasing as it will move on the interval AB. Now, as per the previous things which we have discussed, that there exists some point C and D which assumes at that point the maximum and the minimum value. So it may possible that this maximum and the minimum value, it is the interior points where the first derivative is 0, the interior point where the first derivative is does not exist, or it will be the end point of the interval AB, because it's saying that it is having the. So what we can say from this, so it has to be closed interval. I should write here, this has to be closed interval. So there will be three conditions for taking. So it may take absolute maxima or minima at three possibilities are: interior point where a first derivative, that means f dash of x is 0. The second one, interior point where f dash of x does not exist. And the third possibility is end points of the interval AB. That means either this maximum value is occur where the f dash is 0. If the first condition is true, then we are through. In the second one, if it does not exist, but it will never be possible because it is given that the function is differentiable. And the third possibility is that the maximum value is exists at the end point of the interval. So the second topic is invalid as it is given that the function is differentiable at every point in the interior of the interval AB. So that's why the second possibility is ruled out from this. Now we'll need to work out with the first one and the third one. Let me write this the argument which I have told you, that as given that the f of x is differentiable on open interval AB, possibilities of 2 is ruled out. So it is not possible. Now we have to work out with the possibility 1 and 3. Now if either the maximum or a minimum occurs at C where A is less than C less than B, then the first derivative test tells that f dash of C is 0 and C is that point. So that is the things, that is the argument for the third one. And if the absolute value, absolute maxima and absolute minima both occur at the end point, and as so what will happen if the both maxima and the minima is occur at the end points, and as it is given f of a is equal to f of b, then it says that the f of a is the maximum and f of b is also maximum. So maximum and the minimum points is the same. So that means the function has to be constant function. So that then we can say that f must be constant. Since f is constant, we automatically have f dash of x is 0 for all. So f of a is equal to f of b is equal to f of c, f of x for every x is in AB. Then f dash of x will be 0 for every point x is in. So therefore I can say that f dash of x is 0 for every x is in AB. And we are through for this. But so that means the possibilities of 3 is also a rule out, that we have given the argument here in this, that if it is consider its maximum or the minimum at the end point, then it will rule out with that. So only the possibilities of now 1 we have to work on it. That means for possibility 1, let say a point C is the function has a maximum value, and therefore, so what is the situation is that C is the maximum value. So what I can say is f of x is less than or equal to f of c for every c in interval b. In particular, what I can say is regarding the left hand limit and the right hand limit at this point of the derivative. So ultimate my goal is to prove that f dash of c is 0. But what is the meaning of f dash of c? That we know that it is limit h tends to 0 plus and 0 minus f of c plus h minus f of c upon h is equal to 0. This is my objective is to prove. So let me see what is this f of c minus c plus h. If it is h plus is here, if it is h minus, then it is c minus h will be there. And since this c is containing its maximum value, that I'm assuming, therefore what I can say is c plus h is less than f of c for any h positive. This is the things we have. So that will gives me f of c plus h minus f of c is negative. And since h is positive, if I divide both sides by h, this is again negative. And if I take the limit h tends to 0 plus, then this will gives me f of c plus h minus f of c upon h is less than 0. And this will gives me f dash of c is less than 0. On the other side, for h is negative, f of c minus h is less than f of c, because f of c gives you a maximum value of the function f. So it has to be maximum for all the value which we have. So therefore this will gives you c minus h minus f of c is less than 0. Now if I divide by h both sides, so if I divide h, then what will happen to this inequality will be interchanged, because your h is a negative value. So that is h which is greater than 0. And if I take this limit h tends to 0 here both side, that is h minus 0 minus, and that will gives me f dash of c will be positive. So here on the left hand side, it's saying that the function is derivative is negative. On the right hand side, or right hand limit is gives you is function is, and function is differentiable, positive. Here it's saying that positive. Since the function is differentiable, it has to be 0. Both this expression will tells you that f dash of c has to be 0. If the limit does not exist, then the function is not differentiable. But given it is a differentiable function, so that's why this the situation we have. And here we have proved this if I have assumed that the function is having the maximum, contain the value. It may possible that a function is minimum, then also we can able to prove that f dash of c is 0 in any of the case. So hence we can say that the theorem is proved here. So I can say a geometrical interpretation of Rolle's theorem. So what we have done is you have a function y, let y is equal to f of x be a graph of the function with the condition that this x coordinate, sorry, y coordinate of this 2 points will be the same as we have plotted earlier also. Let a comma f of a and b comma f of b are 2 points on the curve. So I will say this is the point a comma f of a and this is the point b comma f of b. So the first condition is we require that a graph is continuous. That means the graph from a to b is continuous. What does it mean? Is we can plot without lifting our hand. The second one, the second condition is required the function has to be differentiable. That means I can say the graph of the function of the function f is a smooth from a comma f of a to b comma f of b, or I can say the graph has unique tangent at any point in between a and b. This is also one can say that. The third condition is required is the x coordinate or y coordinate of a and b are equal, or I can say a y intercept are equal. That also one can say it. Then geometrically what we can say, then there exists a point C in interval AB such that, so there exists some point which is interval AB, or I can say the point C comma f of C in between A and B. That is also one can write instead of this. So instead of, so there exists a point c comma f of c in between this capital A and capital B such that a tangent at c comma f of c is parallel to x axis. So that is the Rolle's-Minway theorem and its proofs and its geometrical interpretation. If you like this video, please press the like button. If you have any comments, suggestion or a question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.